So now we're going to shift from congruence to talking about binary operations. So first we're going to look at some binary operations that are familiar to you. We're going to look about addition and multiplication of integers, and we're going to think of that, what that means for that to be a binary operation. We are then going to eventually work towards defining precisely what a binary operation on any set is, not just integers. And then we're going to discuss how we will handle binary operations from a mathematically practical point of view. So we'll have like a theoretical point of view just to make sure that everything is above board, and a more practical point of view of how we're going to actually use our notation. So let's think about what the essentials of addition and multiplication are to us, because depending on the context, it can mean a lot of different things. So first of all, they have very specific meanings to us. So for instance, if we're adding numbers, integers, that could be combining two separate quantities, right? So if I'm thinking about 5 plus 2 equals 7 means, it could mean that I have 5 bananas and I'm combining them with 2 other bananas to get 7 bananas altogether. For instance, also multiplication can be count the number of ways that we can combine sets. This isn't the only way you can do multiplication, but for instance, if you have 3 different sandwiches that you can choose from and 4 different salads, then 3 times 4 equals 12 tells you how many different ways you can combine a sandwich and a salad into a combination for lunch. And there are lots of other ways that we can interpret addition and multiplication that are very meaningful to us when we're solving specific problems. But I also want to say that addition and multiplication have a much more general structure. So if we sort of ignore for a moment the very specific meanings to us in solving very specific problems, they sort of have this general pattern that we can see. So for instance, each one of those, actually both addition and multiplication, they take 2 different numbers, put them together, or sometimes 2 of the same numbers, put them together, and then convert them into one single number. So if you think of what 5 plus 2 is very abstractly, you take 2 numbers 5 and 2, you combine them in some way, and then out pops the number 7 as your single number as your output. And this type of operation can be done with any set. It doesn't have to be numbers. You can literally have any set in a variety of ways. You can just make up a rule if you want. It doesn't even have to make any sense. And if you think about what this is, I mean, you can think of those 5 and 2 as inputs to something, and the 7 as an output that has kind of a feel of a function to it, right? Operation takes 2 inputs and gives 1 output. Now the 2 inputs, that's not normal for a function, but the 1 output certainly is normal for a function. So with this in mind, let S be literally any set. It doesn't have to even be numbers, right? What should we demand if someone told us, here's a binary operation on that set S that kind of satisfies the same kind of general structure that we were talking about in the previous slide? Well, first of all, the binary part is important. And binary means 2, right? And that means 2 elements of S should be inputs for each computation. If I'm doing an operation, to give me an output, I should need exactly 2 inputs to do that. And our output should literally be just 1 output. So you get 2 inputs for your binary operation and 1 output. There should be some type of closure going on. If I take 2 elements of the S and do the binary operation of it, I shouldn't get something outside of S. The output should literally be an element of S. And what that looks like is a function with codomain S. Codomain meaning your outputs are going to be elements of S. But the domain is a little bit tricky because you can't have 2 inputs to a function. So the question is, how do you take 2 inputs of a function and make them look like 1 input? Or maybe look like, maybe sounds a little sneaky, how do you make them actually be 1 input? And the way we can do it is something that we learned back in Math 210, and maybe we've seen in some of our other classes. If you let A and B be 2 sets, we can turn those 2 sets into 1 set by taking their Cartesian product. The Cartesian product A cross B is the set of ordered pairs where the x-coordinate, the first coordinate, is A, and the y-coordinate, the second coordinate, is B. The first coordinate is in A, the second coordinate is in B. So if we think of the two inputs as an ordered pair, that makes those two inputs becoming one input. Two separate inputs becoming one ordered pair. So this gets us closer to defining what a binary operation is on a set S. The inputs are ordered pairs. So our domain is, and the ordered pairs, each of them, each the x coordinate and the y coordinate are both elements of S, because those are the two elements that we're combining. So our domain is the Cartesian product S cross S. And so we can let S be any set, and a binary operation is literally any function f going from the Cartesian product of S cross S to S. So if we wanted to express the addition of integers as a function, which isn't something we usually do, and we're just doing it here actually to sort of show you the connection between how we do addition and how we can think of addition as a function. Well, we can define it as a function. I'm going to call it A for addition, from z, the Cartesian product of z cross z to our codomain being z. And A of xy is equal to x plus y. So we're taking the two elements, putting them in x and y, putting them in an ordered pair, x comma y, and the output is x plus y, which is a single number. Now, of course, in real life, we do not express binary operations as a function. I mean, I'm not going to stop you from doing it if you think it's fun. But usually what we do is we put a symbol between the two inputs to indicate the operation. Putting the symbol between the two inputs, that links those two inputs together. And so they're sort of operating as an ordered pair, right? That symbol is operating as like linking them up as an ordered pair and telling us that we want the output under the binary operation. So for addition, we use the symbol plus. So the operation if A comma B is our ordered pair, then A plus B is the operation on A and B. And for multiplication, we use a lot of different things, but for instance, we could use a dot, or we could just put them next to each other. Then the operation on A and B is A dot B. We actually do these on other things too. I mean, not just numbers. You've actually seen this done when we do composition of functions, right? What does a composition of function do? Well, we use that little circle function, right, or circle symbol to indicate the operation. But and the binary operation is on some appropriate set of functions. We got to make sure that the codomains and domains are matched up appropriately. But the operation on a function f and a function g, that's a pair of functions. We take those two functions and combine them to make f circle g, which is one function. So if you find yourself defining a binary operation, you can use any symbol that you want, right? That you find helpful. It could be one of the ones that we've seen before, or it could be some symbol that you just make up. All right, so now I think you're ready to work on the activities for Introduction to Binary Operations. That's on the PDF file included with this video.